Good evening, sir.
Ha,
Am I audible?
good evening, sir. Good evening. Yes, sir. Yes, sir.
Yeah.
Uh,
Thank you.
so, uh, uh, we start. We can
Yes, we
start.
can start. No issues. Yeah, we can
Yes,
start.
yes. Okay. Thank you.
So,
Thank you.
yeah, let me just
Uh,
adjust my
uh,
screen a little bit.
yes.
Then give me just 2 minutes. Yes, sir. Please go ahead.
Okay. So, Mr. Rohit Prajapati, Technical Director, Digitoid Technologies, Bangalore, uh, holds experience in embedded system, IoT, and artificial intelligence, with over a decade of experience in designing and developing innovative solutions. He specializes in creating production-ready embedded software, proof of concept (POC) for IoT applications and as AI system. As an educational consultant, Rohit collaborates with university to bridge learning gaps, delivering impactful training programs in IoT, embedded AI, and wireless sensor networks. Currently, he heads the Embedded Artificial Intelligence Education Program in partnership with the STF Microelectronics, empowering the student to build their ready skills. About the digitoid technologies, Digitoid Technology is leading provider of cutting-edge hardware and software solution for industries in data acquisition and analysis, automation, test, measurement, real-time monitoring and control, as well as many other applications. And partnership with STM Microelectronics, France, Delegate Taiwan, uh, Mentiswave Networks, Vedya Technology, Chemo Instruments, UK. So we invite Mr. Rohit Prajapati for
Yes, sir.
the expert speaker. Please, sir, you can start.
Yeah, thank you. Thank you so much, Ravish, sir. Thank you for
Uh,
such a warm introduction, and thank you for giving me this opportunity to take a session for 90 minutes, I probably guess, right? So,
yes.
and I definitely thank all the participants who has taken out time to attend this session. And
And
I believe that
participants
yes,
from all over India. They are from Tamil Nadu, Kerala, and then Maharashtra, Gujarat. So all over India. Okay, sir.
definitely.
Thank you.
Thank you so
Thank
much. Definitely, I mean, it's a wonderful platform to share the knowledge about IoT system. Especially today, I will be talking about the ecosystem that will help anybody who is working on IoT systems to add machine learning and AI applications on the edge itself, right? So I have just a short PPT which I would like to go through to create the foundation of the topics that I am discussing today. And at the end, I will show you a demonstration or maybe probably an application, a real-time application on how machine learning can be deployed on IoT nodes. Okay, so this will be a part of industrial IoT application. So let me share my screen quickly. Please let me know if at any point there is maybe if you cannot hear me or cannot see my screen. Please give
Sure,
me
Sure,
that.
sure,
sure, sir.
Yeah.
sure.
So I would like to share my entire screen. Then I will move into the PPT mode. Okay. So is my presentation visible?
Yes,
Yeah. Okay. Thank you.
yes.
So today I would like to share this presentation, which is getting started with Edge AI applications using the ST Edge AI suite. So a brief introduction about digital technologies. So we are a core embedded system solutions based company based out of Bangalore. We started in the year 2018. And we focus on distribution, system integration, which is more about software and hardware applications, custom applications. We also focus on upskilling training programs and e-learning. So we work both with industry and academics. We have today we have collaborated with 200 plus colleges throughout India for different programs, especially in the domain of embedded systems and emerging technologies, such as edge computing, AIoT, industrial IoT, vision AI applications. Then we have sensing and data logging, right? Wireless applications. So there are different verticals where we are working with several engineering colleges throughout India. So we understand the current trends that is emerging from the industry side, as well as we also understand the gaps that the educational institutes, especially the engineering colleges in India, faces. Right. So we are somewhere trying to fill that gap through our offerings. And for this, we have partnered with several OEMs, or let's say the technology providers, such as ST Microelectronics. We have partnered with National Instrument, Digiland, a Taiwan-based company. Then we have partnered with Timitech, which is again a Singapore-based company for wireless applications. So close to 6, 7 companies are there with whom we are working very closely on different domains. Getting started with the topic, so we all understand that for any IoT system, right, sensing is the first step, right? So any IoT systems do make use of some form of sensors. It can be any type of sensors, but without sensors, we cannot imagine an IoT system largely. So usually sensors allow us to collect different type of real-time data from the surrounding, and maybe with this data we would like to make some meaningful decisions, right? And we also know that today we have billions of sensors, right, deployed across the continents, throughout different countries, right, different applications. Billions of sensors are there out in the field, which generate huge amount of data, right? Now the next challenge is about how to make this data useful for certain decision making processes, right? And this is where we step into the next logical step. So when it comes to adding intelligence into IoT systems, right, or let's say decision making capabilities to IoT systems, the first step is sensing. Sensing is the point where we can collect different types of data, right, and the raw data from the environment and different processes or systems. The next step is about making use of this sensor data for logical decision making, right? So sensor nodes are made intelligent and self-aware by adding AI. So uh, today we have this AI today we have this technology, right? Or let's say we have tools, we have different types of uh, development environments, which allows us to quickly add machine learning and AI capabilities to systems. Now, the overall fundamental objective of this is to to make the systems more intelligent and self-aware, right? It can be a low computing device, or it can be supercomputers also, right? But yes, any form of computing device, we can add intelligence to that. Now, as we understand, AI deals with algorithms, which are nothing but these are mathematical models which try to mimic human behavior based on the knowledge acquired from its past experiences. So we need models, or we need computer mathematical models. We need data so that these models understand what the data looks like or can be trained on the data. And this is where we move into the intelligent systems. Now, if we just think about an IoT ecosystem, right? So let's say that we have a sensor node. The sensor node collects data from the sensors and it streams the data to a cloud infrastructure, right? And maybe the user, in the form of a PC or some handheld mobile devices, they can access the data from the cloud. So typically an IoT, let's say, application looks similar to this. So if it would be a traditional AI approach, what would happen? The nodes would collect different types of data. This data would stream to the servers or the cloud applications. And if you want to do any decision making, you would have to do it here, right? Once the data is available here on the cloud infrastructure. So this is the traditional approach. But with traditional approach, there are several challenges which we will look into the next slide. right? So if I would have to talk about different types of challenges in this, the first challenge would be about let's say since the data is continuously streaming to the cloud, the first challenge let's discuss maybe would be about data latency, right? So the time we collect the data, the time we push the data to the cloud, and the time the data is processed in the cloud requires some time, and that time taken is known as time, the latency involved in the system, right? So sometimes this data latency might not be desired, okay, because we might need to process the data quickly, and collecting the data on the node level and processing the data on a cloud level might not allow us to maintain the real time decision making capabilities, right? So first challenge might be the data latency. The second challenge might be the power consumption of the nodes. So these nodes mostly are powered by batteries. Usually the IoT nodes are designed to be powered by batteries, right? We don't, most of the times when we deploy IoT sensors nodes, we don't have the flexibility of connecting it to some continuous power supplies. Rather, those are battery operated devices. So the consumption of power at the node level is directly related to the data transmitted to the cloud, right? Because it's a wireless, most of the times it's a wireless communication, right? Maybe you might use MQTT or some other protocol, HTTP protocol, but yes. So thing is, the more the data it streams, the more will be the power consumption, right? So battery power consumption is one of the key challenges of IoT nodes. So this is the second challenge. The third challenge would be about data security issues. Since you are collecting different sensor data and sharing it with the user through via a cloud medium, so maybe whenever the data leaves the device, there might always be chances of the data getting corrupted or maybe accessed by some in an unauthorized way, right? So these are three fundamental challenges: the data latency, battery power consumption, and the data security issues, which is inherent to any traditional IoT based systems, right? Now, to overcome these challenges, we do this edge AI approach, right? Now, in edge AI, the entire ecosystem remains same, but the only thing that changes is instead of processing the data or maybe applying machine learning on the cloud, we do it locally on the device, right on the node itself, right? That's why it's known as edge AI approach. Now here, the data is collected by the sensor nodes. The data collected in real time is processed by a machine learning model locally on the node itself, and the decision data is shared with the cloud. Remember, here the decision is shared with the cloud to the user, not the data itself. It's not the raw sensor data, rather it's a decision data. Now, this decision data is not shared always. Okay, it's not a continuous stream of data. It might be shared at specific occasions, right? So likewise, we restrict the amount of data shared with the cloud. In the process, we restrict the chances of data getting corrupted or maybe accessed in an unauthorized way. We also reduced the since the transaction between the sensor node and the cloud is limited, we also restrict the power consumption issues and data latency issues. Data latency issues because the data is processed by a machine learning model right at the point where data is collected, right? We are not doing it here, we are doing it locally here. So this is also known as embedded AI or local AI approach, right? So this is the advantage of moving your decision making process or machine learning right on the node rather than on the cloud. And today my demo will be focused on this only, right? Now, most of the times, people think that in order to run machine learning or AI, we need huge resources, computing resources. No, that's not true. Okay. So it all depends on what type of application you are doing and what type of results or maybe what type of, let's say, performance you are expecting from the system. So most of the times, if you are working on, let's say, sensor-based data, right? Multiple sensors, single sensors, it can be examples of wearable devices. It can be examples of healthcare monitoring systems, right? So whenever you are working with different types of sensors or data coming from the sensors, you don't require very big models or enormous huge size models. So these models can be run by a microcontroller itself, right? A low power microcontroller. So this is where the edge computing or edge AI approach is built around. So today we have different types of microcontrollers available in the market, based largely based on ARM Cortex based architectures, right? And these architectures are very suitable for running machine learning applications, because at the end of the day they have inbuilt uh, hardware multipliers are there, MAC units are there, which are highly suitable for processing the data. And on the other hand, today we have microcontrollers which comes with neural network processors or neural network accelerators also, right? So the industry is rapidly shifting from let's say traditional microcontrollers to AI powered microcontrollers also. So today we have a lot of offerings with us, and that allows us to readily deploy machine learning models. Now, what could be the next challenge of an engineer who wants to design an AI powered IoT system? The next challenge would be about the ecosystem, right? So what type of software development platform, what type of let's say machine learning models? I don't have an experience in machine learning. I'm a good embedded engineer or IoT engineer, but I don't have experience in machine learning. So how to develop the machine learning model and deploy it on the hardware? That is the challenge, right? How to get data to train your model? So there are several challenges when it comes to machine learning development and deployment on a hardware level. So for this, I would like to go to the next slide and discuss about the ecosystem, right? Now, before that, we would like to understand, why do we actually need AI in embedded systems or IoT systems, right? So there are two types of approach. One is the standard programming approach, which is rule-based approach. Okay, the other is machine learning approach. Okay, where the rules are learned from the real world data. So standard programming is where you as a user, right, or you as a developer, write the rules, and you tell the code or the algorithm or the device to act according to the rules, isn't it? Whereas in machine learning approach, what happens? We don't write the rules, rather we provide the data. We develop a model which can understand the rules from the data, right? So this is an evolving process, isn't it? You can change the rules and you don't have to rewrite the code. Rather, the model would evolve to understand the rules from the input data. But this is something fixed method where the rules are fixed, the rules are limited, and you don't have that flexibility of changing the rules, right? So today, with the help of machine learning, we can solve so many different types of problems which was not possible using standard programming method, right? So this is why machine learning has become so popular, and we do need machine learning in resource constrained devices such as embedded systems, or maybe let's say IoT systems powered by embedded microcontrollers. This slide explains about the distributed AI approach. So if I have to explain this, so this shows that we have billions of edge devices, right, which are powered by ultra low power devices and sensors. So it can be your home equipments, let's say a washing machine, it can be a drone, it can be a coffee maker, it can be a smartwatch, it can be a drilling machine, it can be a robotic arm, air conditioner, security camera. So day-to-day use objects, right? These are powered by microcontrollers, right? On the other hand, we have gateways. So all these devices today can exchange data with the cloud infrastructure through gateways or micro data centers, right? And finally, we have this cloud infrastructure, right? So if you see that we generate huge amount of data from everyday use objects and these low power devices, and this data needs to be processed, right? We cannot push all the data to the cloud, rather it needs to be processed locally on the device. And when we enable the power of decision making to the devices itself, right, and this is how the decision making process is decentralized or distributed, right, and it is very efficient. So as I said, these are few of the benefits of using AI at the edge. ultra low latency, more reliability, security of data, privacy by design, sustainable on energy, right, and better user experiences. So this has been discussed. This slide tells few things about the possibilities of edge AI. So let's say in home maintenance system, this example gives an idea about a dishwasher. So let's say the dishwasher is not draining properly because the belt inside the dishwasher is not performing, or it has become old, or there are some problems with that, right? So you can, with the help of edge AI, you can find out you can detect the problems inside the dishwasher and maybe uh, could be efficiently, you can diagnose the problems and maybe solve it, right? We use edge AI a lot in industrial maintenance systems where we have to find problems within the machines, industrial machines or industrial setups. This is a security application where we can use machine learning to find out if window break incidents has happened or not. Let's say somebody is trying to break the window glass break incidents and all. In restaurant, we can make use of different types of ultrasonic or lidar sensors to find out to go ahead with people counting and all, right? So these are few of the possibilities, but yes, wherever you use sensors, wherever you use microcontrollers, processors, you can make use of machine learning and edge AI there. So it can be applied to any ecosystem as long as you are using the sensors to get the data. This slide speaks about the ST Edge AI suite. Now we are moving from the topic of bringing Edge AI into the systems to what tools we can use, right? So largely, I am taking help of ST Microelectronics to present this slide because we are working very closely with ST to offer different types of programs for the students and engineering colleges and institutes based on Edge AI. And the first tool that I would like to discuss and which we have used extensively for our application as well as for educational purpose is the Nano Edge AI Studio. So if you go to the ST website, we will see that we have ST Edge AI suite. The first one is Nano Edge AI Studio. So Nano Edge AI Studio is an automated machine learning design solution. So basically, it features somewhere close to 5 million combination of libraries, which are pre-built libraries, right? So I would like to share one success story here. We were working with one of the engineering colleges in Mysore, and it was a mechanical department, right? So as we understand mechanical department, they do use different types of sensors like vibration, load cell, and different types of other types of sensors, right? Uh, but usually their curriculum is designed in such a way that they don't have a lot of expertise in programming, or maybe let's say the focus is not there, right, on algorithm development and all. So if let's say there were a group of students who wanted to understand how they can use machine learning for their mechanical related applications, right, maybe finding out the analyzing the vibration patterns and all, right? So what we did was we offered this solution where the students need not develop machine learning model from scratch. Rather, they can collect the data, and I will show you how easy it becomes for anybody without machine learning background or without any expertise in AI and machine learning. They can quickly develop machine learning models on real-time sensor data and deploy it on the hardware, right? So very ideal solution for people who are getting started with edge AI and maybe want to go ahead with development of POCs and prototypes. The next tool is Cube.ai, which is again from ST Microelectronics. Now, this is for advanced users who are familiar with, let's say, using Python-based frameworks for development of machine learning models, or maybe let's say neural networks, right? So if you're using, let's say, TensorFlow, you're using Keras libraries, you're using scikit-learn, PyTorch, MATLAB, right? And you're familiar with these frameworks. Now, if you have a model developed and trained on these frameworks, you can deploy the same model on your STM32 target also, or hardware, using the cube.ai. So here yes, you know about machine learning algorithm development, you know how things work, and you know how to train the models. Then using cube.ai, you can train your custom models and deploy it on the hardware, the STM32 board, right? So this is also very useful when it comes to uh, developing some edge-based applications. So in today's session, I would like to. There are different types of boards from ST Microelectronics. Okay, but largely I would like to focus on one board, which is an industrial IoT board. So this board is known as ST Evaluation ST Win board. Okay, and this basically is an has been designed for evaluating industrial IoT applications for Industry 4.0 or something, right? And this is a very small board, and it's just the size of a it's the size of a ATM card, let's say. Okay, smaller than that, slightly smaller than an ATM card itself. And best part is it features a STM32 processor here, microcontroller, which is based on ARM Cortex M4 architecture, and it features your different types of sensors are available. I will quickly show you the list of sensors also that is available, such as 3D accelerometers, gyro, IMU sensors, audio sensor. Everything is populated here only, right? So we have pressure sensor, light, temperature, humidity sensor. So basically, it is used for deploying this IoT nodes on industrial machines and collecting the data from machines, right? Now, this board also has some pinouts which allows you to connect external Wi-Fi and Bluetooth modules. Okay, so this is a node, but to add Wi-Fi functionality to this node, you require additional smaller boards which can be interfaced with the pinouts here, right? And this can truly be a real-time industrial IoT node development platform. And we are working with few colleges in northern India where they are developing a POC based on this for industry 4.0 based applications. So moving ahead, this is a workflow, Edge AIoT development workflow. So basically, if you want to get started with AI and IoT, right? So what you have to do, the first step is about data preparation. You need to design a data logger first so that you can collect real-time data coming from the sensor for different systems. And this falls under data acquisition and data processing. You do these two things here. Next is model development, right? So once you have the model, once you have the data with you, you can go ahead and you can develop the model. So model development means the machine learning model. So you can make use of Nano Edge AI Studio, like I said before, or you can make use of, maybe you can develop your custom Python based models, and you can make use of cube.ai also. The third is model implementation. So before, yeah, so here in step number 2, in the model development phase, you develop the model and you train your model on the data that you have collected, and you test the model also, right? So model development, training, and testing is taken care here in step number 2. Okay, and in step number 3, you deploy the tested model on the processor, right? So here what happens is basically it's the inference phase. So in machine learning, we have two steps, right? The training phase and the inference phase. So we take the trained model, we deploy the model on the processor, and we expect that device to make use of that deployed model and do some decision making, right? And finally, the node, which has the possibility of connecting to a cloud service such as AWS or Microsoft Azure or custom servers also, right? You can do it. So basically, the decision making happens here. And once decision making happens, we can connect that to some cloud infrastructure, and you can share your decision making data with the user. So this is basically the development workflow that any developer, or maybe let's say anybody who wants to work in AIoT systems, is required. Now I would go to the demonstration part. So if you have any questions so far, please let me know because I am done with the presentation. I will move to the actually it's a demonstration because I would like to show you how the tools are being used, right? To go ahead and see like exactly how it works in real time. Any questions are there from the participants? I am open for questions related to the topics that have been covered so far.
Sir, there is questions in chat box.
Acha, then I
One
have
question.
to go back to the
Uh, there is one
yes.
question. Sir,
Okay.
I have doubt IoT experiments where we access the LEDs or RGB LEDs remotely.
IoT. Remotely through different
Hmm.
portals like Adaptive iCloud, we don't use any kind of sensor in real life to all the IoT devices use sensors of most of the devices. See, basically, yes. So mm, basically, when we say about IoT devices, right? So two possibilities are there. One possibility is that let's say you have an IoT node at your home, right? And you are sitting in your classroom or you are sitting in your office, right? And you are interacting through a mobile phone with your IoT device that is in your home. The IoT device is in your home and you are interacting with that IoT device remotely from your office or classroom. Let's take this scenario. Now, what are you expecting with this IoT device? Either you might want to monitor the things in your home, right? And if you want to monitor what is happening in your home, you would require sensors. Yes or no, right? So if you want to see, like, let's say if there is any gas leakage in your home, right? Obviously, you would require some type of gas sensors. Or if you want to monitor the air condition in your home, or the yeah, so if you want to monitor before you reach your home, if you want to monitor that, okay, the air condition or the everything is set in the home properly, right? So obviously, you would require some type of sensors. On the other hand, there is control that you would like to do, right? So once you get the data from the IoT node about your home environment, you would also like to control, and that is where control, like you said, right? You want to control LEDs, RGB, or different IO portals through a cloud infrastructure, through a mobile phone. You can do that. So typically, IoT systems can have sensors only, can have control only, or they can have both the things, right? It depends on application. But yes, if you want to do AI on the IoT device, right? Definitely that time we need sensors. And most of the times this is what brings value to IoT. Let's say you have a smartwatch, isn't it? A smartwatch is a very good example of IoT device. So when you use a smartwatch, just getting the heartbeat data, okay, or let's say some body parameters is not enough. What about if that data tells you more about your health conditions, right? And how would that become? So once your body parameters are collected, and if your smartwatch is powerful enough, it runs very powerful machine learning models, AI models, to tell about the health conditions based on the data that is coming from the sensors on the smartwatch, then it would definitely add value, isn't it? So the value addition happens through sensors, the value addition happens through uh, maybe processing the data which is coming from the sensor. So that is the reason why I said that in most of the IoT systems, sensors are used, because that is how the actual value in the application comes from. Otherwise, without sensors, also there are so many applications you can make use. If you just have focus on, if you just want to do the control part, not the sensing part. Okay. Do we have any additional questions?
Yes, anyone else?
Okay, I think I
Okay.
should move to.
Yes, sir.
Yeah, yeah. Thank you so much. Okay, I think I will move to the sharing my screen and to the demo part. One minute, I'm not able to share entire screen. My screen is not shared, right, sir?
Yes, yeah, yet not shared.
Not shared, right? Because I'm not
No,
able to
no,
share. I'm
no.
clicking on the share button. It is not getting shared. So I'll go to share, screen window tab. This site will be able to see contents of your, let's say, this one. Okay. I'll stop it once again.
Yes.
Yeah, 1 minute, sir.
Yeah,
I'm just
yeah,
checking
it
one.
has. Okay, okay.
Yeah. Actually, I just shared only the window. I wanted to share my entire screen.
Okay.
Entire screen. No entire screen. Okay, yeah. Sorry, I was making a mistake. Now I think it is shared. Yes.
Yes.
Yes,
Okay.
yes, sir.
Yeah.
Yes, sir.
So I was not selecting that the actual window to be shared.
Okay,
Okay.
sir. Okay,
So
sir.
in this demo, we are going to discuss about anomaly detection technique, which is one of the very popular approach for condition monitoring, predictive maintenance based applications in Edge AI. Anomaly detection is all about finding irregularities in the data pattern. So basically, anomaly detection model, what it does, it let's say you have a data set, right? So anomaly detection model finds out what is normal in the data and what is abnormal in the data, and this difference that anomaly detection technique brings in, right, plays a very important role in finding issues or problems within the system. So for example, in this case, what we are trying to do is we would be, yeah. So let's say taking the example of this small picture here, right? So let's say we are trying to monitor a pump. And how do we monitor this pump? So basically, this has a rotating device, and we place a accelerometer, or let's say, yeah, accelerometer or a vibration sensor, and we get that vibration data, and we apply anomaly detection model to tell that what is normal vibration and what is abnormal vibration. So usually when a pump is operating normally, right, or any machine operating normally, the vibration patterns will be as usual. And let's say if there are some problems, and there might be different causes of the problem. So it can be because of maybe issues with the motor, issues with the current supply, issues with the material of the device, and all those things, right? As soon as there are some issues within the machine, right, or let's say in this case the pump, the vibration pattern changes over a period of time. So from normal, it deviates, and at that point, the machine learning model or the anomaly detection model identifies the deviation, and it it gives you a result, right? It gives you a similarity score, which tells you that okay, by what percentage the vibration has shifted from normal. And that is very important, okay, because that data can tell you what is the issue in, what is the let's say what is the maybe the measure of issue in the machine, or what could be the potential problem that has caused that vibration shifts, right? So this is largely used in ecosystems such as industrial maintenance, we call it, okay, or factory automation also. There are different types of setups, and wherever, right, in any system, it can be engine of a car, it can be maybe aeroplanes, it can be any type of machine you want to monitor. You can make use of anomaly detection technique, right? So the overall objective of this demo is to make use of Edge AI to use anomaly detection model right on the microcontroller itself. So we are not doing it on some PC or something. The model will be deployed on the microcontroller. Okay, and this decision making capability of what is normal or what is abnormal in the real time data coming from the vibration sensor, right? So the data will be input in real time. The model will be trained to understand the normal vibration pattern, and if there is any deviation from the normal, the algorithm will detect it and give you a similarity score. So let's see how to do this. So for this, I would connect my, I will just do one small change here. I'll turn off my video because it's the only thing, one camera I'm using it. So I will just share my camera feed. You can see. Can you see the camera feed, sir?
Yes, yes, sir. Yes, sir.
Okay.
It's visible.
Okay. So here. Okay.
Visible, sir.
So, yeah. So if you see here, this is the same board that I was showing there, the industrial IoT node. I'm not using any pump or something, so I'm just using this fan. It's a DC fan. It can be run in three different speeds: speed number 1, speed number 2, and speed number 3. So using a double-sided tape, I have just placed this node on this fan, right? And I have powered this node also. Now this node is programmed in a data logger mode. So as I told you, this industrial IoT node already features different types of sensors. Right now, in my application, I will be using 3-axis accelerometer. Okay, so basically, this node is programmed to use onboard 3-axis accelerometer and collect the vibration of the fan. So let's say I will run this fan in speed number 4, speed number 3. So the fan is running in speed number 3. Obviously, the fan, when it rotates, it generates some vibration pattern, and that vibration pattern is collecting through this USB cable and pushing it to the PC. So we have SD card modules also there. If you want to store that sensor data on SD card. But right now, I want to log that data. So this is the setup. And
Sir, your voice is not coming. Excuse me, sir.
is it audible now, sir?
Not properly, sir. Mitesh, can you please make sir presenter again?
Yes, sir. 1 minute. સર મને એવું લાગે છે કે સરની બેટરી ઉતરી લો હતી તો સર
No,
ડાઉન થઈ
maybe
ગયું
પાછું
લાગે.
એમને he has joined the meeting again. એમને પાછું જરા કરી દો.
ઓકે સર.
પ્રેઝન્ટર કરી દો.
હા યસ સર એ કરું. ડન સર.
Okay, okay. Yes, sir. મિતેશ જરા ચેક કરને પાછું હજુ નથી વોઇસ આવતું.
ઓકે સર, આપણા તરફથી કમ્પ્લીટ છે સર.
ઓકે ઓકે ઓકે.
Hello, now is it okay?
Yes, yes.
Okay, okay, okay. I
Yes,
think there was an option of.
Yeah, sir.
ठीक है, okay. Let me share. I think this was muted.
No, now you are audible, sir.
Okay, so now let me start back.
Yes.
Visible, right? Okay.
Yeah.
So this is the industrial IoT node setup, and here we have the industrial IoT module. I have attached this module to the fan because for this demo, I would like to show the vibration pattern of this fan. And if I try to introduce some disturbance to the fan, the anomaly detection model will detect it. Okay. So this demo is based on anomaly detection model, which is widely used for predictive maintenance, condition monitoring applications, right? Finding out what is normal and what is abnormal in the data. So for this demo, I have used vibration sensor here. I mean, it's already there and I have enabled that sensor. It's basically a 3-axis accelerometer. And I am collecting the data through this cable to my PC. I can also store that data on an SD card available here. But for this application, I am collecting this on real time to my PC. I will start this fan. Bit number 2. Okay. This is the application, the Cube ID application, where I have already, this is from Steam. So in this application, there is a program here. This program is basically a data local program. So what I'm doing is I will deploy this program. So I will go into data local. So basically, I will be going in data. Just run this. So these codes are readily available for the students. For every sensor available on the IoT node, we have a code for that to access that sensor, get the data. This is for 3-axis accelerometer. So I have already programmed and let me see the data on a serial console bit. Yeah, so if you can see this slide, so this is the accelerometer data that is coming from the sensor, and this data is in a buffer size. Okay. So how do we collect? What is the structure of this data? The data is collected in a format. Right. So we have 56 samples per axis. So we are collecting 3-axis data and stored up. 768 samples we are collecting and we are pushing it to the right. So at a time 768 samples are being data I need to collect in my, and I need this data for developing the machine learning model. So what I will do is I will use NanoAI Studio. So this is NanoAI Studio, the software platform for developing machine learning applications. And if you see, NanoAI Studio has different projects: anomaly detection project, and class classification, single class classification, and extrapolation. So today I will be interested in using anomaly detection technique. We have a class classification where you want to categorize your data in different categories. Single class means single class. Extrapolation is largely based on regression-based application, prediction-based applications. So for this project, what I will do is I will go ahead and create anomaly detection model, right? Let's see this one. And I will deploy this and give this project a name. So basically, let's say test. And we'll do target selection. So which is my target? It supports STM, it supports third-party microcontrollers, it supports Arduino boards. So many different types of platforms are there for which you can develop your machine learning model and deploy it. So today I'm using STM. So here my part is STM. So we have this one. Okay, just select this. The confirm. Right, this is my project. And it features the memory of 640 kilobytes of RAM, 2 MB of internal flash. There's different types of capabilities of the boards, and it's an ARM Cortex M4 controller. So,
Sir,
yes.
sir, your voice is very means low, कम आ रहा है सर voice.
Okay, अभी?
हाँ, अभी ठीक है.
Okay, I think वो fan जब चल रहा है ना, so because of the fan that noise is coming, that is why.
Okay.
Okay, वो PC के बहुत पास में है, just make it little bit far away.
Okay.
तो इसीलिए okay, उसको मैंने थोड़ा दूर कर दिया ताकि इसका noise ना आए. थोड़ा PC को दूर कर लेता हूँ. Okay. अभी ठीक है ना आवाज?
हाँ, अभी इस इंटेंसिटी से अच्छा है. ठीक है.
Okay. ठीक है, ओके, मैं डेमो कर लेता हूँ. अच्छा, बैकएंड से ले रहा है ये. Now, how is it?
Yes, very fine, sir.
It was selected. It was taking from the webcam.
Okay.
So कम आ रहा था. अब ठीक है ना? Okay.
Yes, very fine.
Yeah. So my bad. Okay. So now we already have run the data logger. So the node. So we have programmed the node with the data logger code. This node is already programmed with the data logger code. So it collects the vibration data of the fan and sends that data to the PC. So I can already see the data on my serial monitor. So this data is 768 samples. Okay, total of 768 samples I'm collecting and pushing it to the PC. Now what I will do is I will make use of NanoAI Studio. So already we have created the project, an anomaly detection project. And since this board has around 640 kilobytes of RAM, 2 MB of flash. Okay, so let's say I can just select my memory footprints. This memory footprint is something which is more about, like, let's say if a machine learning model is selected, right? What should be that size of the machine learning model when it runs inside the STM board? How much RAM it should consume, how much flash memory it should be occupying, right? So let's say ideally I will give 64, and here maybe let's say I will give 92 or 128, let's say double of that. Okay. Sensor I will use 3 axis accelerometer because that is my sensor. and I will do it. Right now, this moves to step number 2. In step number 2, I can do add signal from serial USB because the data is coming from the node, right? Data is coming from the node. So now I will select the COM port, right? And let's say I will start collecting the data, something close to 200 samples. So 200 lines of data, each line 768 samples, right? And this is the regular data. So this is the normal data that data collected under normal vibration pattern. So I have not started the fan. Let me start the fan at speed number 2. And now I will start collecting the data, right? So you can see there is some vibration patterns being collected here in NanoEdge AI Studio. And this is the vibration pattern that is coming from the fan running at speed number 2. Okay, so this is the setup. Now we have 3 axes. Pink represents Z axis, we have blue Y axis, and black as X axis, right? So this data is being collected incrementally 40 to 43, and we are just selected 200 lines of data. So we will wait for some time to collect the data. I will just show this data logging process for you to get an idea how easy it becomes. So you just have to write a data logger code. You have to place that IoT node on the machine or anywhere from where you want to collect the data, and you can collect the data on SD card module, or you can also collect the data directly on the PC, right? So likewise, we can collect the data, and let's say just I want to stop the data collection here and continue. You can also preview your data here. Okay, so you can preview your data, how it looks like, what is the data in the tabular format, and you can import this data. You could import this data and you can name this data as normal vibration, right? Normal vibration. Okay, so this is the data that you have collected. So 84 lines of data, 768 samples per line, per axis 256, and it will also check whether there are some empty lines, numeric values only, so many different types of things you can check. Okay, this is the visualization of your data that you have collected. So what I did was, because it takes some time, right? What I did was, already I created one project, same type of project, accelerometer project, if you can see here, right? The same project I have created. Regular signals I have collected. This is the normal signal. Then we collected abnormal signal. How did we collect the abnormal signal? So in abnormal means we have to show, like, if let's say external disturbances. So from serial USB, then start collecting the data. And in this case, what I will do is I will introduce some disturbances. Okay, I will do these disturbances, or I can even maybe disturb the fan. Okay, you can see the disturbance. These are manual disturbances just for the sake of reference, that what is normal and what is abnormal data. So in real time, the abnormality can be because of the blade of the fan having cracks. It can be any type of abnormality, right? But just for the sake of manual disturbances, I'm putting some disturbances and I'm collecting the data. And this data also I can import, right? This data also I can import, isn't it? So likewise, I have collected, I will not save this right now. So we have collected regular signals. You can collect multiple regular signals for different conditions, and you can, let's say, for different speeds. Right now my fan is at speed number 2. For speed number 1, for speed number 3 also you can collect regular signals. You can collect multiple abnormal signals. Right now, one regular, one abnormal we have collected. Next, we go to the benchmark process. So benchmark process is where the magic happens. Okay, for example, if I run new benchmark, right, it asks me whether I want to consider the signals that I have collected under regular and under abnormal as for the benchmark process. So if you collect multiple regular signals and multiple abnormal signals, you will get this option for multiple signals also. Right now, only one is there. You can start the benchmark process, right? So once you start the benchmark process, what happens internally, it connects with the NanoEdge AI cloud and it tries to scan different anomaly detection models and it gives you the performance of the models also. So the benchmark process is to find out the best anomaly detection model, because right now your project is anomaly detection project based on the data set that you have provided. So it finds the model. How does it find the model? It tests the model. Sorry, first it trains the model, then it tests the model, then it evaluates the model and gives you the performance parameters, right? So let's see what are the performance parameters in the benchmark process. Internet connectivity, where it went. Okay, I think some issue in the benchmark. Let me run that once again.
It's very interesting, sir. Nice demonstration, sir.
Thank you so much, sir. So I think why it is not working. Okay, so my project was accelerometer. We were in benchmark. Okay, so something happened. I will not wait because we are running out of time. So I will just close this one. If anybody is interested, maybe get back to me. I can share some videos on how benchmark works. But right now we will not run it from scratch. Yes, I will delete this one. And this is the benchmark that we already created. Just you have to run the benchmark. It will load and it will show something similar to this. Okay. So basically in this benchmark process, what happens? We have tested, I mean, this benchmark ran for 2 minutes. If you can see here, we have 2 minutes here, search duration. During these 2 minutes, 25 libraries were tested and the best library had this accuracy of 92%, and that library or the anomaly detection model, if you would deploy it on the hardware, it would consume 2 kilobytes, close to 3 kilobytes of RAM when it is running, and 2.7 kilobytes of flash memory. So we have 640 kilobytes of RAM in the microcontroller. It just uses 3 kilobytes, right? We have 2 MB of flash memory. It just uses 2.7 kilobyte. Just see the size of the machine learning model that is generated here. So with this um, constraints, we can definitely deploy this model on the hardware, right? And overall score is 89, but we have seen that anomaly detection model can go up to 98, 99.9% accuracy also. We have one more parameter here, 80 iterations. So this 80 iterations is minimum learn cycles. So basically to train this anomaly detection model that is shown here, it requires 80 cycles of training. Okay, 80 training cycles. Each cycle needs 768 samples of data. Okay, so 80 iterations, all this information you get. Now this graph that you get here, right? So this has so many red dots and blue dots. Now all these red dots are nothing but these are the anomalous data, or these are the disturbances in the data, right? Anomaly data basically. And all these blue dots are the normal data, okay, regular data, and these are the abnormal data collected under abnormal signals. Now the goal of the anomaly detection model is to create a boundary between regular data and abnormal data, isn't it? So a ideal model, or let's say if the model would have been 99.9% accuracy, you would see all these red dots at the bottom end, all the blue dots on the top end. So there is a threshold at somewhere 90 here, similarity score. And what is this y-axis? This y-axis is nothing but percentage score of similarity or similarity score. So how similar the data is with the regular data? So all the regular data should be pushed up and all the anomalous or abnormal data should be pushed down in an uh, good accuracy based models. Okay, but right now it's 92, so we have a lot of abnormal data in this zone also, if you can see, right? Now what we would do is we would move, this is the benchmark selects your best machine learning model. Okay, now we will see what are these 25 libraries selected by this tool. So if you go to validation, it lists out all the libraries and it lists out the score, it lists out the accuracy, it lists out the RAM, flash, uh, learning iteration, everything, right? And it also gives you the execution time. So if you want to run this model, it takes 9 millisecond. There is 1.6 millisecond and all those things also. It also gives you the name of the models, zero score model, MML, IPC, and all those things. Okay, but it does not allow you to, let's say, uh, change the parameters of this model. These are pre-built models, right? It comes as it is. The only option is you can select, if you don't want this selected model, which is selected as here, you can select this model, this model, this model. You can change your data and you can run the benchmark again for best models to appear, right? So it's an iteration process. Okay. So quickly, now let's say that this is the model that I have selected. I want to test this model. What I will do, I will go, you have an option of report also. I'll just quickly show this one. If you want to download report of this model, you can download this. It gives you performance, cross validation, okay, what data, confusion matrix, everything it gives you. And it gives you algorithm flowchart also. So you can go through this and you can use all these things in your paper, or you can use it for your project purposes also in your report. Now let's say if I want to test this model on the PC itself, I will do this emulator. Okay, now this emulator allows you to test the model, the anomaly detection model coming from based on the data coming from the sensor, or the setup that I have done, right? This setup. This setup. So I will first, it's a dynamic model. The anomaly detection model is a dynamic model, which means that I can train it on the go. So what I will do is first I will select this, right? I will give here somewhere 90 cycles. 80 is the minimum iteration, but I have given 10 extra, and I will do start learning. As soon as I press start learning, the data coming from my setup, right? The data logger code sends the acceleration data to the PC, just like how we did the data collection. The same data will be used to train my model for 90 cycles. So I will do start, right? So the training has started. If you see, the model's knowledge is getting incremented, okay, or it is learning, the model is learning, okay, and this is the setup. The model is learning the vibration pattern of this fan set at speed number 2. Now the model is on the PC and the training is happening on the PC, right? So it will train up to this threshold, that is, sorry, not up to this, up to 90 it will go, because 80 is the default one, minimum, and I have set it at 90. So let it go up to 90. Let's wait for some time. So step by step, and you can see here the data coming, right? So this is the data that is used. 768 samples, 768 samples, 768 samples. Every time, every increment uses 768 samples of data. 256x, 256y, and 256z axis. Now the training is over. Now I will go to detection model, detection phase, right? Go to detection, and I will start getting the result from the model. Now this result also uses the data. It takes the data from the board and it detects. And it shows, right now you can see the similarity score is 100. The reason similarity score is 100, because there is no, this is the normal vibration pattern of the fan, right? There is no abnormality in the data. But if you see, as soon as I start disturbing the setup, right, with some, right, you can see the similarity score reducing. right? And if I release, it should go back to 100. If I disturb, the similarity score reduces. And if I release, it goes back to 100. So you can see the model understands the disturbances. 100% similarity means there is no disturbance. And whenever there is deviation, the similarity score will reduce and it will show by what percentage the deviation has happened. If similarity score is 70%, this means that 30% is the deviation from normal, right? So if let's say the blades of this fan has some cracks, obviously the vibration pattern will change and this will result in the deviation of the similarity score, right? And using some if else conditions, we can easily send notifications through maybe through Wi-Fi or something to the user to tell about the errors or the problems happening inside the machine, right? Now, let's say we are happy with the performance of this model. What I will do is I have to go to the deployment phase, right? So I will close this emulator. This is very important. See, most of the times when we develop machine learning models, most of the people say that, okay, let me run this on the hardware, then I will check whether it's working or not. But that should not be your approach. Your approach should be when the model is developed, before deploying it on the hardware, you should test it, whether it's working on real-time data or not. And this is what emulator gives me the power. So right now I have an idea that it works fine in the emulator. So I will go compile library and get this library. If I get this library, so let's say I will just put something like this. Okay, the library has been compiled and ready for download. I will save it. And let's say I will go to downloads and I will save this. So this is the library that I have downloaded. I will extract it. Right. Yeah. So if I extract it, I get nanoagi.h as a header file. I get .a file. It's a C static library. So this is the actual model implementation, libnia.a. And this is my header file, which I will be using to interact with the functionalities available here. So these two files that I downloaded from the studio, I can import this in my embedded project. And I can use this as library, just like you use Arduino libraries, right? Similarly, I can use this, and this entire thing is in C. Okay. So now the next step would be the deployment part, right? Because I have tested it on the PC. I have downloaded that library also. Now my next step is about deploying that model on the PC, right? So this comes to this step, right? Model implementation. So this data preparation, model development has happened, which means model selection, training, and model testing. Now model library creation is also done. And this is model inference. So model inference means running the model inside the hardware. So how do I run the model inside the hardware? I have to go to this CubeIDE project. So the same project which I have created an option of adding the model here. Okay. Yeah. So if you see here in source file, I have added this libnia.a, the one which I downloaded, and in INC, I have added this nanoagi.h, right? So these are the two files, isn't it? nanoagi.h and livnia.a. So this was already done previously. So I'm just not doing it again. So these two files, I have included it in my project. So these two files. So basically my overall project, this C project, will make use of these libraries. And in runtime, I can explore these libraries from the device. One small change I have to do here is my code is in data logger mode. I will run it in inference mode. Okay. So for that, I have to go to one line here. Yeah. So I will just comment out this data logger mode and I will uncomment this inference mode. So simple control I have done here. Now I will run this. Now I am deploying this code inside the microcontroller. Okay. So basically I am deploying this library inside the microcontroller, the anomaly detection model in the microcontroller itself. Now it got programmed. The board is programmed with the anomaly detection model. I don't need my PC or I don't need any additional tool to run that machine learning model. The model is deployed on the hardware. And in real time, the model is getting the vibration. Sorry, the board is getting the vibration pattern of the fan. Okay, first it will be trained. So the board is getting the vibration pattern of the fan, and the model gets trained on the samples, and the anomaly detection model also gives you the same similarity score, right? The decision making happens on the device itself. So what I will do is I will show you the result on the serial monitor coming from the board itself. So let me open. For serial monitor, first I have to make sure that my NanoEdge AI Studio is not accessing the board. Then I will go here and I have this one and I will just turn this on. Okay. Okay, so let me reset the board once. So as soon as I reset, it will start with the training cycle. Okay, let me just reset the board. So I have reset it, right? So if you see that now training cycle has started, so it will go up to 80 cycles and the code is written to go up to 80 cycles. Okay, so 80 cycles of training is happening. Yeah, so you can see the similarity score is 100. I'll disturb it. Okay. So if you give some disturbance, it's very sensitive. If I release it, it goes back to 100, right? So if the similarity score changes, this means that it detects that disturbances, it detects the deviation from normal vibration pattern. If similarity score is 100, means there is no problem within the machine. It is working as required, and there are no changes. Now here we are using only one type of sensor, right? That is the vibration sensor. There are applications where you can integrate vibration with temperature, humidity, current, different types of sensing. So it can be a multi-sensor application also. Your anomaly detection model can work on data that is coming from multiple sensors at a time, because combination of different sensors might result or say might the combination of data coming from different types of sensors might be representing the different states of the machines, right? So that time you can make use of different types of sensors only. Just to make it simple, we have done it for only vibration sensor. Now the best part is that the model is deployed on the hardware, and the similarity score or decision making anomaly detection is happening here, and through this I am communicating it on the PC. I can also change to speed number 3. Okay, let's say speed number 1. If I change, it just detects some different speed. Speed number 3 also I can change, and I can train my model on speed number 3 also. I'll just reset it, and again it starts getting trained on speed number 3 data. Okay, now the training is happening. The training is again happening on the device itself, on the board itself. Now you see again it's 100%. If I start giving disturbances, it reduces. So sometimes people ask me a question that, sir, I can use if else condition to check, let's say, whether disturbances are there or not. But usually it is not recommended because you cannot reproduce different types of operating states of a machine, right? With how many if else conditions, how many switch case statements you can write? Very few, isn't it? So instead of working on individual data points, the model works on an array of data points, and it tries to understand the pattern hidden inside that array of data points, and it tries to learn that array of data points. Okay, so if you are using if else condition, you can use only on one single data point. If x-axis is greater than something, y-axis is less than that, right? You cannot work on an array of data points. So the best part about machine learning with sensor data is that you can train your machine learning model to understand the pattern hidden inside the sensor data points, which can be an array of data points. And with this, you can design application based on anomaly detection. You can do audio classification. We have boards which from ST Microelectronics which supports vision applications, condition monitoring, predictive maintenance, right? Regression based application. So there are so many different ways of using machine learning on the hardware on resource constrained device such as microcontrollers, which is known as embedded AI or embedded machine learning. Now, once your decision making happens on the device, you can connect an Wi-Fi module from here, and you can send that decision data to the user also. So that was the demonstration from my end. And if you have any questions, you can let me know. I am open for questions.
Thank you, sir. Thank you. Very interesting demonstration, sir.
Thank you so much.
If participants have any
Any
question,
question?
they can ask.
Yes, definitely. I'm open for the questions. So I would suggest all of you to explore this NanoEdge AI Studio. If you have an Arduino board also, you can go ahead and use it. It's a free
Okay.
tool available from ST website. Maybe
It's nano. Sir, can
I
you
will
write on the
just,
chat box?
yeah, definitely. Let me, it's a free tool. Just you need to provide your mail ID and you can register it. There are good tutorials also.
Okay.
So if you want to explore machine learning quickly for your microcontroller, you can do it.
It can be used with the Arduino and
Arduino
this
also
thing.
third party like ST boards.
Raspberry Pi
Raspberry,
might be different, right?
I'm not checked it, but yes,
Mm.
Raspberry Pi is basically a processor. So
Yeah.
here the idea is about microcontroller based systems.
Okay.
So
Okay.
yeah, I think you can go ahead with Arduino, readily available Arduino boards and all.
Okay.
I will share one link also here. Just please go to that for use cases. Very good resource from ST's website.
Okay.
You can go to case studies. You can find so many different industrial case studies using NanoEdge AI Studio and Cube.ai. And it will be definitely very useful for students, for faculties, even faculties. You can go ahead and share this knowledge with your students so that tomorrow they can use this technology in their project. I have shared that link also. Please go
Yes.
and
Yes, sir.
see that one.
Yeah, and sir, basically we are processing that time series, correct? And
Correct. Yes.
yeah. So, do we need some advanced signal processing technique or something? Because as we, yeah.
Correct. Yes. So usually, I mean, raw data is also sufficient here because
Yes,
the
that's
tool
what.
itself includes some form of, I mean, frankly speaking, we have not used a lot of signal processing until unless it's an audio signal. Okay.
Okay.
Sometimes for audio signals, little bit of signal processing or filtering might be required. But so far we have done audio classification applications. We have worked on different types of sensor data. I mean, if it is raw, it's good. There is no problem. Raw data you can work on. For vision, yeah, we need to do some transformations, for vision-based applications. But again, right now, though, it's time series data. So your question is based on that.
And
So
sir,
raw data can be used. Yes.
and sir, what about the time window? I mean, when we are observing a time series, we are observing, for example, 200 points at a time. Right?
Sampling window, you are saying, right?
Sampling window, exactly.
Yeah.
So
So
we are shifting that window, right?
correct.
So
Yes.
meanwhile, we may lose some data if. So
Yeah. So
what is the way
basically,
of selection of
yeah.
window?
So basically, what happens is, let's say if you have a sampling period of,
Mm.
sorry, sampling frequency of 1K, right? So 1000
Okay.
samples per second, right?
Right.
But you cannot create a window of 1000 samples because
Exactly.
filling that buffer will have some latency or maybe overheads will be there, right? So usually
Exactly.
we start with 128 samples, okay, 128 samples. Then we increment it to 256. Ideally, what we do is 512 samples somewhere halfway between, right? So there will be some data which might not be collected during switching process, right? Or from one buffer, from first data collection point to the next one. But usually, since it's not a very high speed application, okay, most of the times we can manage that. But if it's a very high speed application, then you might want to integrate some RTOs or
Exactly.
something like that to take care about this data missing issues. But usually, most of the times, over the period of time, let's say you collect 1 second of sample data, okay, in the buffer, or let's say 0.25 seconds of sample data in your buffer point. So it works fine, not an issue. And most of the times it's a work of iteration also. Sometimes you feel that, okay, 256 samples will work, but when you go for the model development, right, you will see that it does not give you proper accuracies and all. So that time you have to come back and again change your data points and
Yeah,
sorry, the
exactly.
size of data points and again go back. So it's little bit of trade-off thing or maybe iteration.
Right, right, sir. We must know the possible highest frequency of the data that we are the application, right?
Yes, yes,
Okay,
yes.
okay, sir. Thank you, sir.
Sir, Industry 4.0 using this AI IoT?
So basically, see, Industry 4.0 is a vast topic, right? But one key like aspect of Industry 4.0 is uh, going beyond traditional IoT. Okay, going beyond data collection and enabling efficient decision making or data-driven processes, right? So for that, edge computing is one topic which enables Industry 4.0, right? So edge computing or edge AI with IoT enables Industry 4.0 in efficient decision-making processes or automation processes. So this entire thing is not Industry 4.0, but it's a component of Industry 4.0. So here what we have shown is like instead of relying, see, normally when you are deploying different types of IoT systems in any manufacturing setup or industrial setup, right? What happens is that data needs to be processed, and most of the times in industry factory floors, we don't. Recently, we were working with one company for project. They don't want to share the data outside the setup, right? They want have to have the data collection processes locally, or maybe they will have local servers, something like that. Now, what we are trying to do here is instead of collecting the data and processing it on the server, we are processing the data locally on the device so that decision making is distributed where it is collected. Okay, decision making processes is distributed, not centralized in one position. Okay, like in the servers or something like that. So this not only like I said, this not only enables efficient decision making, but also reduces data latency, power consumption issues and all those things. So it enables more efficient data decision making processes from the data over the period of time. So it's a component of Industry 4.0. We do require
And
other aspects also for a full-fledged
sir,
Industry 4.0. Yeah.
sir, in demonstration, you have mentioned that if we give 30% disturbance in model, then it will show.
Yeah.
Means what is limit of that disturbance?
Okay, so there I was not saying 30% disturbance. There we had the similarity score, right? The maximum
Yes,
similarity score.
similarity score. Yes,
The similarity
but
score is 100%, right? Whenever you get a similarity score of 100% from the model, this means that there is the data that you have trained, sorry, the model that you have trained on the data and the data that
Matches.
you are
Okay.
getting, both are same, similar, 100% similar. Now, let's say you trained your data on normal vibration, but there is some problem within the blade of the fan or some problem within the machine. And now the data that is trained is different and the data that is coming from the sensor will be slightly different. Deviation will be there. So this anomaly detection model detects that deviation and gives you, let's say it will give you 70% similarity score. Okay.
Okay.
Once the blade is or once the disturbance is there. So this 70% similarity score means the model understands that the data pattern coming from the sensor is 70% similar to the trained data and 30%
Okay.
deviation is there.
Okay.
Okay. So it depends. It can be as low as 0, completely dissimilar data points, 0 similarity score, or it can be the same 100% similarity score, and it can vary anywhere in between. So you can write conditions like if similarity score is less than 40%, raise the alarm.
Yeah, based on the
Yeah.
applications.
Correct. Yeah, raise the alarm or send notification to the factory manager, something like that.
Okay.
Participants, if anyone have question, they can write their question in chat box or they can raise their hand.
Yeah, it seems only coordinators are asking questions.
Yeah.
Okay.
Anyone, please? Or maybe later on you can send us the question. We will try to get back to this.
Definitely. And anybody wants to connect with me, I'll share my email ID. So
Yes,
Rohit.p
sure,
at,
sir.
if you are working on some project and if you are working on some similar things, then definitely I would request Rohit.p at
No,
digitotech.com.
it's very interesting, sir. Uh,
Yes. So anybody who is working on embedded systems, working on microcontroller based systems, working on IoTs, they can definitely benefit from these tools. Okay. And maybe these are the few possibilities that I can show you here in my office space. But real world, the possibilities are huge. So that is why I shared you this link, right? The use case link. If you go there, you can see so many different industrial real world applications being solved by these processes, right? So definitely I would request all of you to explore these possibilities.
sure, sir.
Yes.
Oh. Sir, one group photo, sir.
Definitely. I'm already live. I mean, the camera is turned on. We
Yes,
can take it.
yes, yes. Participant, please turn on your camera for group photo. I am taking data, sir. Okay, sir. Okay. Fine.
Thank you. Thank you so much. It was really a pleasure putting forward this technology and sharing this information with all of you. And I look forward for connecting once again or maybe in future programs. Please feel free to reach out. Okay,
Sure,
we will
sir.
be
Surely,
there
sir.
Sure.
Surely,
with
sir.
other kind of applications. We have a lot of tools, right? So thank you so much, and all the
Thank you.
best. And it's a really very good initiative where you create such a platform where faculties from different parts of India are attending and sharing the knowledge with industry people and all. Definitely, it's a really I appreciate this a lot. And please keep continuing doing this great job, bringing the industry and academics together on a common platform. More such programs are required in future. And thank you so much for making me
Thank you.
being a part of this wonderful journey. Thank you. Have a great night
Thank
ahead.
you, sir.
Good
Nice to
night.
have
Thank
you,
Take
you,
sir.
sir.
care.
Thank you.
Thank you.
Same here. Thank you
Thank
so
you, sir.
much. Yeah.
So, participants, we will meet again tomorrow. It's very interesting session, I think. What about you? You can mention in your chat box. Please write something about
It's
session.
nice to see you,
And
your family.
they are writing, I mean, excellent session. Okay.
Okay,
That's
you may
good news
sign
for
off.
us. Okay. So we will meet again tomorrow at 6 p.m. Please connect around 5:45 so that we can start session in time. Okay. Thank you. Good night.